Hello again. Good afternoon, everyone. Here we record the recitation Math 102 for week 11 lab. So here is the outline of the presentation. We will solve the exercise at the end of week 10, and we'll talk about trigonometric substitution, and we'll start talking about partial fractions, which are mainly sections 8.4 and 8.5 from our textbook. So we will cover two examples, and we'll leave one exercise for next week. So first of all, we start by the exercise at the end of week 10 presentation. And here we were asked to evaluate the integral from 0 to pi over 4 of x tan x secant square x dx. We start, as usual, by uploading the file for week 11, which is this file, week 11 exercise, and week 10, and trigonometric substitution and with partial fractions. And we'll import the packages and functions needed as usual. Don't forget that here we are using, from SymPy, we are trying to import everything at the beginning to avoid any issue later on. We'll define, first of all, the variable x using symbols as a real variable. And since from our integral, we see that we have x tan x secant squared of x. So here our choice is to take x as u. So x is u is x. Derivative of u is called du. And we consider dv as tan x times secant squared. Why this choice? Because we know that derivative of tan is secant squared. If the derivative of tan is secant squared, one can assume that we can already tell that, well, it's like u times u prime. So previously we had u to the power 2 multiplied by half. So we'll define v as the integrate or the integral of dv. Okay, so our result using directly the by-partial integration would be just uv evaluated at pi over 4 minus uv evaluated at 0 minus the integral of v du from 0 to pi over 4. You can force the execution here using the do it command, and this is what we should get, minus half plus pi over 4. If you go to the Jupyter notebook file, it's much more clear. We just got the res as the result of the by-partial integration formula. uv evaluated at pi over 4 minus at 0 minus the integral of v du from 0 to pi over 4, and you get minus half of pi over 4. Okay, we could explain it a little bit more why we got this, but maybe we don't think it's worth it here. The main goal is reached, which was to show how to perform by-partial integration if needed using pi. Okay, so we'll continue with the new material, which is example 1 from the trigonometric substitution section. And here in example 1, we have the integral of square root of x squared minus 9 over x cubed. And here one could observe or recall that tan squared is secant squared minus 1. Why we are doing this? Because we observe that under the square root, we have x squared minus 9. So with a proper constant in front of the x squared, well, we could say that, well, this could be converted to a trigonometric integral. And this is exactly what we are doing here. So what we are doing here is that we will assume in our integral that x is 3 secant u. If x is 3 secant of u, it means that x squared is 9 secant squared. So what do we have under the square root now becomes 9 times secant squared minus 1, which is 9 tan squared. Wow. So we could easily remove the square root, taken into account that the tan could be positive or negative, and we'll have a beautiful integral. And this is what we are doing here using the transformation command or transform command in Python. So we'll start first of all by defining our integral as I. Keep track of the names here used. Our integral is the integral of square root of x squared minus 9 over x cubed. We'll produce an evaluated integral. We'll display I, and this is what is displayed, thus I. And we'll define u as a new symbol using the symbol command from SymPy, which is true. And we'll transform our I, our integral, using the I dot transform. And this is the new command transform that performs the substitution, that transforms in I x by substitutes x by 3 secant u. This will substitute x by 3 secant u. And we'll have a new integral called k, and we'll display k. So this is k. What you see here at the bottom of the slide is the new k, okay, before simplification. So now we can use a substitution. The substitution z equals tan u to get a simpler integral. So you can see that two possible results can be obtained, since we, depending on whether z is positive or negative. So we'll define z as tan u, okay? So tan u will be replaced by z, and we have a new third integral after transforming again k using this substitution. So this substitution will replace tan u by z. So this is our integral L now. We have the integral of z times absolute value of z over 3 times z squared plus 1 squared. So the result depends heavily on whether you allow or not z to be positive. And if you want to simplify it, you see the 1/3 is a common factor here. So first integral, possibly if z is positive, you get z over 2z squared plus 2 minus arctan of z over 2. That's when z is negative, sorry. Otherwise, if z is positive, you get minus z over 2z squared plus 1 times arctan of z over 2. So these are two possible answers, allowing whether or not you want to allow z as the tan of u to be positive or negative. Okay, so that's for question 1. And since we didn't have any precision here in the example, so both answers are acceptable. Now, for the second example, we would like to evaluate this integral from 0 to 1, integral of x squared plus 1. So what is the idea? If I see that I have under the square root of x plus 1, I can think that x could be substituted by tan of u. So we'll have integral of tan squared plus 1, which is integral of secant squared. And being careful with the sign, I could just write as integral of just secant. So this is exactly what we are doing. We are defining I as the integral of the square root of x squared plus 1 from 0 to 1. Then in I, we substitute u by new symbol u as tan u equals x. So we'll transform the integral I using the transform command, and x will be substituted by tan of u. So instead of having an integral of x squared plus 1, square root of x squared plus 1, we'll have integral from 0 to pi over 4 of tan squared plus 1 to the power 3 over 2. One could question why I don't have only the square root of tan squared plus 1. What happens here? If you define x as tan of u, dx is tan squared plus 1 du. So dx would again bring tan squared plus 1. That's why you have 1 tan squared plus 1 to the power half coming from the square root, and another one coming from the du. So we'll have half plus 1, which is tan squared plus 1 to the power 3 over 2. So basically, this is what we get, integral from 0 to pi over 4 of tan squared plus 1 to the power 3 over 2. And the tan squared plus 1 here is for sure secant squared. Secant squared to the power 3 over 2 is just secant cubed. And this is what the slide is saying. Therefore, we get automatically after integration, before integration, the integral from 0 to pi over 4 tan squared plus 1 to the power 3 over 2, which becomes just the integral, if you want to simplify it, of secant u cube from 0 to pi over 4. So L is this formula, ln of square root of 2 plus 1 over 4 minus ln of 1 minus square root of 2 over 2 all over 4 plus square root of 2 over 2. Okay. And finally, we leave this question about partial integral of partial fractions or rational functions for next week's presentation, which will be week 12. Thank you very much again for following, and we'll meet again. Goodbye.